higher level class, right? So this higher level class. The reason why I say that is because if you go and you look up bays, you'll find that there's an original paper that was constructed based upon bays, and it uses the Latin terms as part of it. Matter of fact, I've actually put that up in the past as a reference. I didn't this time because it's not focused. What I find is that semester to semester, I adjust what I consider to be the most important parts of it, and getting you to understand some of the terms is important, but not all of them. So while you would come across that in like Bayesian decision theorem, you're not always going to come across it in modern textbooks. So,
okay.
Even 5 to 10 years ago, that was the common, and now it's not as common. So it's changed. There used to be an emphasis on understanding the origin terms. Give me just 1 minute. I'm going to go ahead and log into Canvas so I can watch this for you guys. Such a process. Find something else for me to talk about.
I mean, we can do whatever. I don't.
I have a set of slides for review.
Oh, you have a set of slides for review. Are they posted?
They will be in just a minute.
Awesome. I don't know. I think I'm having one of my broken lines here. I mean, that very well might be. Okay, so I'm done for that. Can't do anymore. I'm focusing my mind and my mental powers. What limited capabilities I have.
I have a 1 ring. How I made a 3 pilot with 1 ring, so it was scary.
That's impossible. You have to have at least 5.
At least
At
5.
least 5?
We have to have an odd number because you have to hold one back for your own like physical, mental regulation.
You have to have one that's allocated to just running all the background processes.
Right.
Keeping you breathing, etc.
That one died a long time ago. In service, how many brain cells did you have while you were in?
I kept all mine, except for the ones they irradiated on a daily basis when the nuclear reactor started leaking or something. There wasn't a day that went by that they were like, okay, stay clear of these bulkheads. There's a radioactive contamination issue. It's like, it's fantastic. It's okay. I mean, if it wasn't that radiation, it was just the lead poisoning trying that we were associated.
They tell you not to drink.
Oh no, the water tastes like JP5. Jet fuel.
Yeah, I
I don't know if that's what actually the water tasted like that, or if it's just because you can smell it in the air all the time.
No, it actually smelled and tasted like that, and they've actually come out and said that they have, they weren't very good at. Well, I think what it was they used the same pipes for certain things because they'd go to water quarters when we would get a replenishment at sea, and I think they used the same pipes that they used for water to transfer the fuel around because they used the fuel for ballast in the aircraft carrier. We'd get like 6 million gallons of it at a time.
Well, just ask Camp Lejeune for the Marines. Everyone's getting compensation.
And other boats have had like toxic chemicals leak into the water supply system. Yeah. I mean, you don't have a choice. That and it tastes funny anyways because they're using reverse osmosis and filtration to filter seawater into fresh water.
And you use that salt-free plate.
Ooh, the rock curve.
Actually, this is just a plot function. So this one's actually going to answer a question that I gave you guys on your sheets. So if you've already done it, this is just me talking to you about what I believe the answer to this question is. And I say provide 2 reasons why we might want to approximate some function f, right, or estimate some function f. There are more than 2, all right, but I'm going to give you the 2 most, I guess you'd say most critical. The reason why I say that there are more than 2 is there is a way of sort of looking at it from the perspective of saying that there's more than just interpolation and extrapolation, right? There are technically more values in that. Time series data doesn't necessarily fall directly in the extrapolation framework, but is a type of extrapolation. So it's outside of the system, but it is, the modeling would be then predictive, right? But let's just go ahead and fall underneath of that. Let's just say that there are effectively 2 things we do. We either try to fill in the gaps of what we already have, meaning that we interpolate, and we start off with some discretized distribution, such as the one shown on the left-hand side on the top there. And by the time we're done with our functional approximation, we have what? We have a continuous function that now provides for us. If we interrogate that function, it will tell us the value of the system at any point in between the recorded data. So it's actually, it doesn't tell us anything about what happens after what's been recorded, but it will tell us, let's say, something about what's happening in here between 3 and 4, right? So we can interrogate the system at 3.25, 3.5, 3.75, and end up with 3 new values at those locations. Effectively, we now have a continuous operation where we can interrogate the function at every point. So what's the value of that? The value of that is that we can now understand the likelihood of events to a certain degree based upon where they're going to occur or what values they're going to occur at. Plus, we can also say, now that I understand the dynamics of the system, I can do what? This is the other part. This is what I consider kind of the third thing. Modeling the function allows us to interfere with it, okay? That which is measured is that which is improved. That's a principal axiom of engineering. So once we can measure it, once we can model it, now we can get in and mess with it. I actually saw something today that applies to this. They have created, ostensibly, I don't know, obviously this is introductory research, but they've created artificial gravity. For the first time, they created a system upon which they can induce gravitation that causes light to bend. All right, that's cool. So how did we do that? We dealt with a bunch of models that we created based upon a bunch of observations. And by those systems, we worked back to that until we could figure out how to manipulate that system. So that's what I say is like kind of the ultimate goal of most of this is once you can figure it out, how it works and operates, then you can figure out how to change it to benefit you, to benefit yourself, benefit humanity. You can also do things like what we were talking about beforehand with predictive characteristics, okay? This is like your likelihood of survival, right, relative to having different metrics, okay? If you have, high-fat diet or drink too much alcohol, smoke too many cigarettes, right? Those are things that are higher likelihood of causing you to have heart disease in the long run, or a stroke, or whatever else, other factors, risk factors. So when I talk about the idea of extrapolation, extrapolate, to pull outside of the system, I'm talking about the capacity of the model to now predict the likelihood of your circumstances and your behavior causing a specific outcome. What's most troubling about that for us? Well, not everybody lives till 80 or 90 years old, right? So what happens is we tend to see that the likelihood of death is tending to increase in this direction. So what happens to the density of the samples? What happens to the number of individuals making up the space after about 65? It starts to go down a lot, right? There's far fewer people there to give us sort of supports to reinforce those notions. I often describe the relationship between points a bit like the model is attempting to kind of span the system, right? It's trying to create a, hold on to both edges and create a structure for us to be able to understand what's happening in between. A bunch of little bridges in between the elements describing the relationship of those points as it has been given within a certain perspective. Now, the bottom section utilizes a visualization that we had in one or two of our plots, but we didn't talk about significantly. We did mention it, and that is the idea of leverage, right? Leverage being a measurement or estimation of a band of confidence around which the model is likely to occur. So what do we see there on the left-hand side? We see that the confidence of that particular plot, roughly past somewhere in the neighborhood of about 500, starts to get real fuzzy. Okay, we say, well, what would happen if it continued to grow? Say, well, it could either continue up, right? The trend could expand, or it could plot down, right? So you're either going to kind of level out, flatten out from here, or it could continue in kind of a quasi-linear fashion from that point. But we notice at that point in time, there's a pivot. And the pivot is because as the density shifts, there's a large enough change in the density across the representation that I get less and less sure, because I have what? I have less and less evidence to support my underlying conjecture. My underlying conjecture is what? F hat. That's the best I can do under circumstances. The less data that I have to reinforce that is going to create less and less certainty as it relates to the understanding of the system that is the model we're creating. Key factors that I want you to rely on here or focus on here are going to be related to principles of modeling, right? How we approach the concepts of models. Mostly it's going to be about error. So how we utilize error to be able to generate these approximations. And I also want you to notice a couple of things about this. This top graph, what's one of the problems with it? Is that likely the output of a simple regression? That's a sinusoid, okay? That's a sinusoid. Could I do a sinusoid? Absolutely. And I'll tell you how I do a sinusoid. I just substitute a sine function for a coefficient, okay? I could fit a sine function to distributional data. So if a linear version is a multiplicative and a quadratic is a square of the input, then the input of another model, a sinusoid or sine, cosine, tangent, any of those functions can be utilized to attempt to approximate the system. All right, but one of the things that's funny about this data is there any error on the right-hand side? No, there's no error at all. That system doesn't have any noise. It doesn't have any variance. It doesn't actually have multiple values at a single points either, which, to be honest, is really a chief target for regression. Regression and machine learning in general is designed to solve harder problems that are more difficult to find a singular solution for. This is probably like an autoregressive or fit model system where we're attempting to try to just sample down to the value. But I give this example because I think it's a visually good example, that it shows, you can sort of see on the left-hand side how that shape is established in a relatively complex curvature, because most of us are used to looking at sine waves. But at the same time, we'd also probably consider that this function would likely, if there was an amount of randomness or variance in the collection of the data, what's the certainty that the values are going to be exactly in alignment with the sinusoid? Almost nothing, right? Go back to our original example, how tall are you? Given what day? How much hair growth do you have, right? What's the barometric pressure pushing down and compressing your spine? To what degree of accuracy? Am I measuring with a laser micrometer or am I measuring with a meter stick, right? Where I hold it down at the bottom and then I put my finger here and hold it up again and try to squint across the top of the centimeter submarks, okay? How accurate am I going to get in an approximation of attempting to quantize the natural universe in my measurement metrics? Those same errors apply to both the collection processes, the production processes, as we talked about variance in the construction and parameters of construction, how long a table is, what the resistance of a specific electronic component is, etc. All those things can be slightly variable by a small amount, right? The model has to compensate for that variance. It has to work with inside of it. If it attempts to learn it rather than attempting to just model the underlying system, we end up with some problems. Okay, let's talk about those problems again. These are things that I think are critical to our discussion, right? We've been talking about these right along, but like I said, I want to highlight and focus on these for a moment. notice a couple of things. It says models will perform well on selected subsets of data, but fail to achieve desired results for additional samples are said to be memorizing rather than learning. Memorizing rather than learning. What is learning then? What is learning then?
Being able to handle future problems based off of what you know from existing data.
Correct. So existing data provides us with some information. And what processes do we utilize here in order to be able to determine the outcomes of this system? How do we know when a system is underfitting? What would be a key factor of underfitment?
I would say one would be if you're performing better on training data than your own, or test data than your own training data.
If you're performing better on testing data than training data, you've probably done something weird. I agree, that would be a very, very high indicator. Or performing almost exactly the same between those two and performing very poorly. Okay, that's what I say is another consideration. It's like performing right around the chance factor, like right around the 50% mark, and having equal performance in both testing and training would probably be an indicator that you've done what? You've fit. Now what's the correlation here with respect to the way in which this underfitting line is operating? Did I say overfit? Underfit. Underfit. I think I said overfitting by accident. You've underfit. What is the coefficient? What is the coefficient of this system?
0.
0. You remember previously we talked about the biasing characteristic being in play, all right? If the coefficient factor is 0, then who makes all the decisions? We have beta naught plus beta 1 of x. If beta 1 is 0, that means beta 1 and x are gone. That means f hat is what? Equal to what?
Beta 0.
Beta naught. That's equal to our bias term. Where's the bias term established from? If x is not involved, it is entirely the mean of y. Entirely the mean of y. It's just going to attempt to slice the distribution, the relative variance or spread of values within y. It's going to attempt to cut that in half, right? What is the y-intercept, if nothing more than a relationship of this attempting to bifurcate or divide in half the likelihood of the distributions? The thing is still incentivized to attempt to try to map the system optimally. The best it can do is attempt to try to create a 0 relationship for this error metric. Where is the error metric going to be minimized? When half the samples are above the line and half the samples are below the line, okay? Anything else is likely to cause an increase in the error from those localizations. That value is actually y minus y bar, effectively. So if you go and look at our equations and you cancel everything out and it has to do with x, you'll end up with y minus y bar, and you'll end up with that as beta naught, okay? That is the null hypothesis. That is an inclination that what is happening. There is no correlation between a change in x and a change in y. So correlation within that system would also be what if this null hypothesis were true? 0. There's no correlation, okay? You crank the knob, nothing happens. That's the way I describe it. It's like it's detached, it's unhooked from that system, it's not affecting it. Now let's flip over to the opposite direction, overfitting. Overfitting. Why do we say that an overfit is fairly obvious within our data processes? Are we missing some information in order to be able to apply that this is overfitting in this case?
No.
Do I have any testing data over there?
We've used it all.
We have used it
Used
all.
the whole data set.
I only have one. I have an error
Oh.
down there. I have one testing data. Okay? This is my leave one out cross validation. Okay? So what happened? Yeah, that is my one singular value, right? So yesterday I said we didn't have one, and then I looked at the slide again and I'm like, oh, look, actually there is one sample right there. Okay? So that little bitty tiny error right there is the one sample that I kept back from the remainder of the samples in order to be able to try to understand what was going on with the system. If that particular sample does not align with the rest of the model, what am I going to indicate? I'm indicating that the model is now memorized. It's literally kept track of every single point. It says, well, if x is equal to exactly this, and is before this one and after this one, then it's this y, right? It literally has like a chart, like it has like a cheat sheet that it's looking at, looking up the plot, okay? How does it do that? We've given it too many parameters, that's exactly the case. You can think of each coefficient as effectively a type of memory location. That type of memory location in a high degree polynomial like this one has a lot of informational capability there, all right? The modeling becomes, instead of attempting to understand the principal function of the system, the true underlying f, without attempting to try to capture all error, right? That's where we're here. That's optimal. That's whenever we realize we've gone too far with error. But in the overfit case, it just says, look, I'm going to capture all error. I'm going to totally 100% minimize all error. What do I have to have for that? I have to have sufficient flexibility. I have to be able to capture the whole thing, okay? It has to be a floppy piece of material, okay? If it has even the slightest degree of rigidity, like this paper has rigidity, I can't do the same thing with this paper because it doesn't have the same degree of flexibility, okay? Flexibility is related to what with regard to the model parameterization?
Features?
Order.
Order.
Yeah,
Okay?
order.
Yeah.
Flexibility is akin to increasing the polynomial order of the system. That's a key factor, okay? It isn't necessarily features. It isn't necessarily features. Let me explain to you the reason why. Because I can have x sub 1 for beta 1, and I can have beta 2 and x sub 1 squared. I can raise a feature to an additional power and have an additional coefficient that then parameterizes that. Let me show you that we are already looking at it. Right here. Right here. The correlation between, this says x2, but let's call it y, okay? The correlation between y and x at the bottom is what? It's now a quadratic. There's a curvature there. So this is what? This is a 1 degree system. This is like a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's like a 12 plus degree system. All right, the reason why I can tell is every time it changes direction, that's effectively an additional degree of polynomial.
Degree of
Okay?
power, yeah.
That's roughly how it approximates. So every time it does a squiggle, every time it goes from going down to going back up, it's gained a poly degree. Meaning that it has an additional coefficient and an additional factorization of the particular feature or predictor, right? That predictor carried to an additional poly. That's just a long additive sequence of higher and higher dimensional versions. Cubed, you know, 4th, 5th, 6th, 7th version of x sub I. So, in this case, I have what? I have a linearity, and then I have a parabolic characteristic, right? And it's added together. It's taking the straight line and then adding a little bit of curve to it, right? At each point, a little bit of the curve is put in. So one straight line, then a curvature, added together, you get slightly curved straight line. Okay? We can do this. We can condition the function by adding degrees of capacity to that system. Its flexibility, it can be 100% rigid, solid material, or it can be made to be just a little plastic. It can stretch, it can shape. Okay? It can either be like those pieces of metal they put on the road that aren't bending much, or it can be, as I said before, like the little floppy microfiber cloth that takes the shape of the container. And we talked about that pretty extensively, about the idea that models are effectively a product of the data that they're trained with. What happens here in the middle, in the optimum space? Well, we're actually trading some stuff off. What are we trading off for? Predictive accuracy relative to consistency of performance for future operations. Notice the error there of the optimum system is shown as being one of the smallest errors within this particular plot. Now, granted, it's only for a single sample, but if we sort of continue on in our minds with how that would look as we extend out, what happens there? We say, oh, well, you know, the likelihood of any data point to fall on that line or around that line is going to be maximized when that line best fits, but not overfits the training distribution. The training distribution needs to get as close to the training distribution as possible, right? This is the price is right. It is as close to the actual value without going over. All right, that is how I always look at it, is a tipping point. Tipping point. In many cases, remember we said that the linearity of the system is probably a massive overgeneralization, right? It's probably an overemphasis on simplicity. What do we call that? We said that there are two kind of things that we want to keep track of in a system. We said it's either a parsimonious or black box, right? So, but as related to those, you're correct. It is bias and variance. Variance not being the distributional characteristics of the data, but instead, actually the performance differences between two different versions of that distribution. So let me do this real quick, because I did this last time and I think it works. If we consider that we have the core data, right, we have one distribution of the core data, we sample out, this is our actual raw data input. We're going to sample out those data, and we're going to create one distribution here, right? So let's say that this is the mean of this distribution here, and this is the mean of that distribution originally. What happened? I had a slight shift. The resampling process, or the sampling process, to create the training data set has constructed a new mean of the distribution, right? It can also do what? What else can it change? If I have the standard deviation of the original distribution, I have some new standard deviation, right? We'll call that the prime, first prime. Now I have a new slope, shape of that distribution, right? The density of it can change slightly, all right? Usually not a ton, but because of the fact that I'm doing, let's say I'm doing 70-30, right? Because only 70% of the data is here, what could happen, right? It's either could be wider or it could be narrower. We can have less systematic variance, right? That's where I say that's the square of the square of the standard deviation, right? So variance is square standard deviation, which the reason why we square it is because it's symmetrical. And then I have another set of samples that I create over here, right? And what's going to happen to those? I'm going to have a secondary characteristic of the standard deviation from a new mean as a result of that system shifted in the opposite direction, right? So one shifts to the right, another shifts to the left a little bit from what the original mean was. Go ahead and put the dotted line there because that indicates the original distribution mean, right? So the new distribution means are over here. So we say new distribution mean is in dotted line, but the old one is here. It's the solid line, right? So this line is propagated here, this line propagated here, right? What happens? What am I seeing? I'm seeing two different distributions based upon the same original data distribution. We can think of this as, if I were to draw it as kind of a Venn diagram, right? I have testing, I have training data, and then I have the global distribution from which the data was sourced. All right, so the union, this is training, union, testing, right? That's the union of those data points. And then you have pi, or excuse me, omega, which is the actual global population characteristic. That's the whole pop, okay? So the whole pop is sampled by this. This is a sample of the whole pop. Then I sample it again, subsample it again. What do I end up with? I end up with a smaller version of the whole global population. So from a sampling theory perspective, what we say here is that this is representative of that, but slightly less informationally dense. It doesn't have as much information. So as a result, we can have slight shifts in those values. But as a result of these both doing what? Originating from the same source, their distributional characteristics are approximately equal. Being from the same source, homogeneous, right? Same source, same genus, same origin. The homogeneous nature of these two distributions means that I can treat the testing distribution as if it were new samples collected from Omega, right? From the original core of the population, the actual population that's being sampled. The argument that's being made here is that if I treat it as if it were new samples, I can assess it as if it were operating in the wild. So if I make a model based upon this distribution and I test it with this distribution, what's going to happen? There is going to be a small amount of the deviation that's from the original data that we can't compensate for. We didn't learn from this data. This information was not available to us. But where does that originate from? Well, we have two sources of what we consider error within the system. So we have an expectation of average performance for a specific value within this system, and we can restate this characteristic as having two underlying fundamental characteristics. First, we have the actual function that created this, and the approximation function, and we're going to square that characteristic. We're going to call the relationship between y, right, f of x is equal to y, and f hat, which would be y hat, right? We're going to create the distance between the label and the inference. We're going to say that is going to be based upon certain assumptions, all right, certain assumptions. I've already described characteristics of the distributions maybe better here than normal, but keep in mind, this is still an iterative approximation, right? This is average. This is a function operating on a distribution. Somebody yesterday pointed out to me that this looks a lot like RSS. And I'm like, yeah, it does. So the only thing that's different between MSE and RSS is that we're taking the average performance for all samples within the set, right? So averaging the performance rather than aggregating. RSS is a full aggregation of the magnitude of all error within the system. MSE is the mean square of that error, all right? It's a singular value that's smaller that tells us what the average length of any of those vectors are within that set. I actually had, try to see if I can find this here. I was going to show you guys a slightly different graph that somebody showed me yesterday. Let me see if I can find it. No, that's not it. Yeah, this one's, we'll have to work with this one for a moment, I think. Okay, I gotta move this now. Why is it doing this? It's so weird because you can have a link to something and you're like, I see this. This is right here, and it won't come up in the search. This one? Yes, okay, found it, finally, sorry. So I have come across a lot of diagrams and a lot of visual descriptions, okay? And I still am astounded occasionally whenever a student sends me something. If you guys ever search towards data science, which is one of the medium distributions, it's really good. It'll show you good visualizations of outcomes. I had never seen this graph before, all right? I'd never seen it because I'd never read this particular article. There are like 10 of them. The reason why I'm sitting here is if you search bias variance dilemma on towards data science, you get a long list of them. I'm gonna put this link out, okay? Because I really, really like this graph. Let's look at the one that we have in our PowerPoint slides, okay? This is the one that I gave you previously. Notice, pretty sterile, all right? We said that we experience a bias variance trade-off related to some curvatures, some set of curvatures, all right? So let's look at the other one that I had provided for you here. Notice it's not quite as sterile and symmetrical, okay? It's not quite as sterile and symmetrical. We actually have two characteristics here. Training error and square bias are highly correlated with one another, notice, all right? So what is the training error as plotted here? That is just the assessment of the properties of the values within training. That's how close those values come to their core values. The biased error is the portion of the total error that is as a result of the assumptions made utilizing that training data. I usually say it like this: you can be pretty safe to make the assumption that bias or square bias is effectively the same as MSE, mean square error, all right? So the more accurate a system gets, I say that's a rough approximation. Don't say that's always going to be the case, but for our use and purposes, it's approximately the same. MSE training, not MSE testing. Why? Why not MSE testing? The model learns nothing from testing. We learn something from testing. The model cannot adapt to testing data. If it does, we've made a terrible mistake. It's no longer testing, all right? That would be like me giving you all the answers to the exam and then giving you the exam, right? What purpose would that serve? Nothing, okay? I mean, I think you guys would think it would, but really process it in your brain. Can I assess your knowledge if I give you all the answers in advance? No.
No, but I'd be assessing how far I was off on.
You perform well, right? You perform well. But what happens when I release you into the wild? Your performance is going to be terrible, right? Because you're not have learned, you will have memorized. Okay? This is the key. This is the key factor. Notice what happens here. We have the generalized test error, right? I give this a B minus. Okay, the top line is not true. That is average performance for the whole system because it is both training and testing averaged together. Testing error is going to have a very different look to it, typically, right, under the circumstances. It's okay. This is good enough, all right? So we'll just consider this to be generalizability, the test error. In the other slide we have, the other examples we have, and most of the other graphics you'll find on this, it says average error, all right? Average error between training and testing. It is the union set train test, all right? So average performance error. What's going to happen with average performance error is that this is actually going to dip down like this. It's going to average this and this. So these two right here, green and black, are going to be averaged together in that slide, right? Total error. See this one here? Total error. This is actually the average between the version that's provided here in the other set, right? The green line there it takes the test part out, and the black, it takes the training part out, right? So since we've decomposed them, now we can see them separated from one another. What's happening here? What's happening here? This is very common. We see this very common. Right here. At the crossover point between what? Square bias. This is as the assumptions increase in their accuracy of the training data fit, we hit a point at which what's happening? The difference between testing and training is assessed here, right? This is the difference. They're less different here, and then they get more and more different here until a point to where the difference becomes the difference becomes maximized, such that after this point, there is more difference between training and testing, right, than is justified by the continued increase in model complexity. This is the point of diminishing return, where we've cranked up the flexibility of the model too much, to where now we're continuing to improve training performance, but notice, irreducible errors on this graph, okay, irreducible errors on this graph. I'm going to go ahead and go back to the other slide. I'm going to show you where irreducible error sits on that. Let's assume that this is totally perfect, Irreducible error is right here. Why? Why do I say that the irreducible error is right here at the bottom, almost a tangent at the bottom of that graph? Because I can continue to increase the flexibility, exactly, I can continue to increase the flexibility, and it will not capture the difference between these two standard deviations, right? It won't capture this little band gap that happens based upon slight distributional differences. Now, what happens as the original plot tends toward infinity, right? Tends toward infinity. You get bigger and bigger numbers. The irreducible characteristics of the system are going to start gradually getting narrower and narrower and narrower, right? Irreducibility is based upon the characteristics of the data set. It's the ratio of the number of samples and their information density, entropy, relative to the complexity of the model system. So as the model system is increased in complexity, if you have enough samples, guess what? You can kind of work out the noise and characteristics from the system. But can you ever eliminate the actual sum of the point to the model difference? No, never be able to get rid of it, okay? You can average it out with MSE, but RSS will still always be high because it's an aggregate number, okay? MSE will reduce, total training MSE will reduce to a point, right, to where it totally zeroes out, and then what do you end up with? No, probably not, all right, an overfit model. I use a term, I talk about it in class, I kind of coined this one, right, to try to get it started. I call it the characteristic divergence. Characteristic divergence. That blue point right there is a characteristic point, right? It's the point of inflection upon which the difference, or the training and the testing performance, diverge. That point, that characteristic divergent point, is the location where we note that we're transitioning, as given in the other plot here, we're transitioning from the underfitting zone, in which the model is insufficiently complex to capture the characteristics of the system, and the overfitting zone, where the model has gotten too flexible, right, or we've put too many free parameters in the system for the amount of data we have, all right? That's where the system has now the opportunity to be able to start modeling the data distribution rather than modeling the underlying function. Effectively, that's trying to learn, it's trying to memorize sigma, rather than learning the underlying F, distribution density function, prior. Okay, like I said, I'll put a link to this one up in just a minute. We talked about this already. We talked about the idea of increasing polynomial fit. You can still have x, and then you can have a square of x. You can do this for a feature, a whole vector. You can do it for however you like. But quadratic models allow us to be able to add in a certain degree of nonlinearity. Quadratics are nonlinearities, all right? So a certain degree of nonlinearity can be encountered or can be created. We had multiple different nonlinearities. One of them was a quadratic nonlinearities related to LDA. So we'll look at this one real quick. K nearest neighbor. Remember this one? All right. So we can use it for either regression, which isn't very common. That's where we use a window, plus and minus from a certain point, or we can use it for a region around the outside of a classification problem. It's just K is the number of samples that are utilized as the support to attempt to make the decision. So effectively, every single point in the data set becomes a local model approximating the likelihood of that particular sample based upon its adjacencies. All right, so you need the data. This is a data-driven approach. We've dealt with the idea of increasing K, right? The overfit model is here because it utilizes incredibly small amounts of neighbors to make an approximation. We notice it's very tight and close to the original system, but way too specific to the characterization. The ideal fit model is somewhere in here, around a K of 10, where we're using neighborhood approximation of about 10. And then the underfit model is actually over here with a K of 100. It is so averaged out that the water has been muddied, right? The water's been muddied because it's just, everybody is taken into consideration. The spatial characteristic of the system, the spatial density characteristics are being ignored because they're effectively being averaged out. This is like blurring. You guys, if you've ever messed with image processing tools at all, right? If you use a blur operation, you notice that the intensity, right, the key intensity of one single pixel, you have a nice hard edge, and you blur it, what happens? The distinction between those elements is lost because you've averaged out the measurements of those regions, right? You've muddied it by averaging it out. All right, logistic regressions, this is getting up to really close to where we just were, so it's not gonna be super long time, but what's the problem with a linear regression related to classification, binary classification?
You're gonna have probabilities below 0 and above 1.
Excellent, okay. How do we compensate for that? Instead of using a linearity, we add what?
A lot.
A nonlinearity, which is based upon the natural number e. This one is actually shifted, right? So the core natural number actually sits around the axis, but we're going to shift it up such that the lowest value returned by the sigmoid function is 0 and the highest return 1. We can shift it around by bias, right? And we can change the slope of the system by adjusting the coefficient of e to the negative beta plus, or beta naught plus beta 1, right? The shift and the slope of the linearity. It works well for cases like this one, where you have heavy degrees of overlap between the classes, all right? But well-separated classes require us to take an additional approach. This is key here to understanding. This is pretty much the only formula you need to understand this. If you can understand this formula, you understand LDA. Take into consideration that a line is being projected upon which density approximations are given for a two-dimensional version, right, in one dimension. So a one-dimensional system is created, a one-dimensional flat line, with density based upon the number of samples that are hitting that line, and the density approximations are given here. Each of those density approximations are given a variance, right? So we want to attempt to do something here. We want to maximize two factors. We can maximize them both simultaneously, all right? We're actually going to min one and max the other, all right? We want to minimize the spread, all right? So we min the spread. That means we put the spread on the bottom. So the sum of the spreads is min. And then we want to maximize the spread between the means of each of those classes. So maximize the ratio of the magnitude. Why do I do the magnitude? Because this axis can be in any direction, right? This can rotate around these two distributions in either direction or in any orbit, right? So we're taking a theta, an angle, shining our flashlight and our plane around the outside of the data points until we get the ideal reflection we want, okay? The maximization indicated here is actually the axis of that ideal projection. So when it's maxed, the projection has become the ideal projection, okay? Such that if I place the discriminant boundary right through the middle of these 2 points, I will have found the ideal delta, the ideal discriminant boundary between those two classes, given that data, and I will do so now as a generative methodology. I'm now not messing with the data points any further. I only need these. I only need mu and sigma of the distributions in order to calculate the ideal position, ideal localization of the linear discriminant. So the linear discriminant works well for separability. Also, look over here on this graphic. We see that as the sigma extending in this direction, right? The variance extending in the horizontal axis here, right? Horizontal axis is what? Nothing, right? But the vertical axis is increasing. This one has static horizontal axis. This one has increasing vertical axis. We actually have to create a curvature for that discriminant in order to be able to make that system operate. Because now we have asymmetry in those two axes that can't be compensated for. So as it goes up, we need a quadratic discriminant in order to compensate for it. This is conceptual. I'm not going to make you work anything like that. But conceptually understand that quadratic discriminants are utilized to compensate for heavy degrees of asymmetry between the distributional characteristics of the system, or the two classes, or two-class type problem in LDA. Right? K-fold, we spent time just recently dealing with K-fold. This is going to be the last thing that's going to be on the exam. I basically just want you to be able to explain to me how it works, right? And maybe why we do it. The main reason why, we want to know what the theoretical upper likelihood in terms of performance is going to be. So we take the average performance across all of those different configurations, right, in which each sample ends up operating as both the in-training and the internal testing system. And by that process, we can approximate the external processing of the testing data. If we have an agreement between our internal K-fold and our external validation, then we're likely that we've agreed upon the appropriate degree of polynomial complexity. This is just an additional tool above and beyond a singular approach to the determination of optimal modeling, okay? So I actually end up, instead of with one curvature, right, where I see this is the optimal value, I end up with multiples of those sort of jittered around with everybody getting to be both the training and the testing, right? Everybody gets to kind of switch places, Mad Hatter style, and everybody gets to get an approximation. So we see several different simulated likelihoods, several different potential realities that could have occurred, and we say that the average of those is likely at the core of our understanding of what the best potential performance will be, and what the ideal flexibility of the model would be when trained upon all the data. So we then go back and train a model with that flexibility on the original training data in order to be able to try to find the ideal fit to the external validation, okay? Good luck to everybody. Thank you for your effort thus far. I look forward to seeing fabulous performance on the exam. I'll see you on Friday.
Yeah.
So, are you gonna get a hold of me when you're all ready to go?
Yep.
Okay, I'll get home and.
No. I don't know why anybody thinks that my example exam is the questions you're going to get on your exam. That's not how that works. Oh, these are the questions that are going to be on the exam? No, they're not. I can make up anything I want. No, they're not going to be that type. They don't guarantee anything. Study everything. Do your other professors go, this is exactly the kind of question you're going to get on the exam. Make sure you study exactly this question. No, they say study it all.
Not, well, I will give a caveat to that, to most of my professors have given us like specific topics. Not like, oh, we've done 5 chapters, read all 5 chapters. They'll go through and they'll say chapter 1, these are the key like 5 sections, or in chapter 2, here's the 3 sections.
I gave you guys a worksheet.
Well, yeah,
I'm
just.
No, what you're trying to say, that's the worksheet version of it. I agree with that. I do that. Matter of fact, the worksheet version is going to be closer to anything we have as questions than that will.
Right.
But you'll also notice that the worksheet's in pretty close alignment with the exam questions as well. You'll see kind of a pattern of what things are going to be the most important. I think today probably would be the best example of what I'm likely to ask questions on. If it falls outside the scope of what we discussed today, it probably isn't going to be a major topic. So, though I will say you do need to be able to at least identify the equations. Right, so you'll know which ones they are and what they're for, but you've got cheat sheets for that, so.
That's basically one of the big things that I like the cheat sheet for, is the equations, because trying to remember all the equations, but not just the base form, but all the variations, and then how you can manipulate them and everything.
Every time I've tried to have people do that, like there's one on there that I ask people to work with user given input, right? Try to like remap the basis theorem and explain how you flip the prior and posterior as part of the assumption for the output. So effectively density and fire.
Right.
And everybody was just like, I don't understand. Don't make me do symbolic algebra, it's too heavy. It's like, yeah, I get it. We probably don't do enough of it in class in order for you to do it on an exam, so usually if it's not something we've done like as an exercise type of thing. But it's mostly about identification, understanding the topics, and like, making reasonable, persuasive arguments with them. But it's gonna be your ability to identify stuff. This is just multiple choice for the most part. Right now I'm playing around with adding 2 questions. I've got 2 questions on there that I'm like, I like these questions, but at the same time I'm like, I don't know if they're. I feel like I'm gonna have to throw them out later. So
Or you could throw one in there as an extra credit, and then we either get
That's right.
all or nothing on it. If we can answer it right and we hit it on the head, we get all or nothing.
As effectively right now, I have 1 page of short answer questions.
Okay.
You don't answer all of them, you pick one,
Oh,
you want to answer. And then at the moment, I'm contemplating adding that you can answer 1 additional of those for extra credit, and that is all or nothing.
Gotcha.
So, but it's gonna be like mostly multiple choice. I do have 1 section, I'm converting it. It was fill in the blank previously, but I think I'm just gonna go ahead and convert it to multiple choice. So, because it's fill in the blank based upon a word bank, all I have to do is take sections of the word bank and put them in
Right.
for the multiple choice.
Right.
So I'm just doing that right now. I was gonna actually I had a student who was gonna take a test earlier yesterday. I had to go home and take care of something for my dad. He's got some difficulties late, but I'm reworking it. I will have it finished. I will be finished with it today. I always work the exams like right up to the edge because I try to improve them, hone them, and sometimes it bites me in the butt. But I think at the moment I'm doing pretty well. 394 is where it really kills me when I'm trying to make adjustments to those questions because I'm trying to improve them, iteratively improve them. And even the slightest modification to them make them unintelligible. So.
I think what caught me off guard on that one was I relied on the length of the exam of the previous semester that you handed out too much, and then when I saw our exam, I was like kind of caught off guard.
They were easier. The questions were way easier. They weren't 5 parts of the same question.
Right.
So it's just the iterative process. So you guys did more homework before they did. You had more practice.
Right.
And thus you had been performing better on it. And I said, well, easier, more straightforward problems rather than fewer multi-part problems was better. But I realized it's probably a little bit longer than it should have been by like maybe 2 or 3 questions.
I confused myself on there because
Everybody did. It's fine. The outcome was pretty decent overall. I'm just having difficulty calculating some of the stuff related to it because I threw out certain questions and then I averaged certain values together for the average performance of the class, and then I changed its admissible values, which allowed for multiple answers in some cases. It's just too much work. It's too much work for me. I was sick last week trying to finish it up while I was sick, made it worse.
Right.
And then when I did put the scores in, I used did I tell you about that?
You said it yesterday.
There's a tool in Canvas that allows you to do apply different metrics to it.
Okay.
And it says on there, changes to the values are like non-commutable. Like when you commit them, you can't reverse it. And so I committed the values, and I actually noted that some students their scores actually went down. Yeah.
Oh.
It forces a curve. Forces a curve. And I'm like, that is unacceptable.
Right.
It's unacceptable. So, from my perspective, I always look at it and say, I would rather have everybody get pushed up a certain amount. Well, I was wanting to try to just add a value, but apparently what I was adjusting for was the band of the standard deviation. So I made the band of the standard deviation very, very small.
And it
effectively
made everybody fit.
It pushed everybody, pushed half of everybody below a B.
Oh.
Oh, wow.
Yeah. Well, how it should work.
Right.
Right? It should center on C's.
Mm-hmm.
So I'm like, yeah, no, forced bell curves are not cool.
Yeah.
They're not cool at all. And so I'm like, well, okay, I have to go back through and rescore all these. What I'm going to do from now on is I'll have two columns. I'll have a raw score column that I can see, and then I'll have the score column that you guys can see. The problem is they do not allow me to add score columns. I can only just mute them where you guys can't see them. I don't get the option to be able to have score columns that are mine based upon computation. There's so much stuff that's wrong with Canvas. It's just insufficient in some areas.
Maybe that's where you should have a TA send like a little note, like develop to dev at Canvas and be like, hey, I need this. No, waste of time.
My TA can barely grade stuff.
Oh, God.
Thank you, Professor.
No,
Have a good
you
day.
guys are-